This is the Fourier series that I'm going to give you problems with the answer, not solution on this. I wouldn't go through this if I didn't feel it was extremely important and valuable. And to be really frank about it, it's practical. A lot of the stuff that you get, at least when I got when I was where you were, it's kind of abstract and it really didn't. I don't know. When I took mathematics, we did a lot of proofs. I had to pick an honor of this. I got invited in this math class. We were doing proofs and we're trying to find new ways of doing derivatives, symmetric derivative. Well, if you're a mathematician, that's your life. I understand that. But I saw no application engineering. What I'm about to show you is very applied. All right. It's extremely useful in the stuff you do. Even though you might not see it right away. So back to Friday's lecture, I ended up saying that if you have any periodic function, it doesn't matter what it is, I'm just going to come up with one like this, any periodic function at all, and this is time, call this x of t, if it is periodic, and I'm going to use x of t here, it can be represented as a Fourier series. That means it can be represented as a sum, an infinite sum at that, of c of n e to the j n omega naught t. And here, I better define some stuff. Most of you know this, but in case you forgot, the length of time over which something repeats itself, if it's periodic, is usually symbolized as capital P. Now, like, that's how long it takes before the signal identically repeats itself. This is for a periodic signal. You all with me on this class? All right. You have that. When we talk about the actual, this is called the, in the terms that you use, this frequency is called the fundamental frequency, I think, in your courses. There may be other terms you use. It's the basic lowest frequency over which things repeat themselves. And it's equal to 1 over the period t. And omega naught is simply 2 pi f naught. So the relationship between omega naught there and f naught is really related to the inverse of the period. You all with me? And you've seen this before, right? Now, then I said, well, if you take a derivative of this, and even another derivative, you're going to keep on getting something where if I take x prime, I'm using this function. That's okay. X prime of t. If you do that, you can see here, between here and here, it's a constant slope. Do you all see that, class? And the slope would be, I better give this a height, make it a, it would be a divided by the on time, and I'll call the on time tau. This is slightly different than the one I did on Friday, but either one is acceptable. You all follow me on this? So that means that this, from here to here, if I take a derivative with respect to time, it's just a over tau, right? That would be the height of this for the derivative. And then at this point, there's a discontinuity. It goes from a to 0. And the way you always identify something with a discontinuous derivative, I mean, something where there's a discontinuity in the time domain. In other words, the derivative is discontinuous is with an impulse function. You all with me on this class? So this would have an impulse function of weight a, only it would be negative. So it comes straight down, it would be minus a. And then it would repeat itself. If this was t, it would just repeat itself. But you can see, I'm just trying to indicate how the thing would repeat itself. You all see that? Now here's something important. I'm going to cover it right here. If I look at this, doesn't this look like just a square wave, right? And add to that a delta function series. Do you all see that, class? It looks like we could break this up and we could say this is identically equal to simply a square wave as such where the square wave has a height of a over tau. And we'll call this, I'm going to do something here. I'm going to label this as x1 prime of t. That will be the first function. I can say it's that. Again, this is with tau. It's that plus, then you would have some x2 of prime of t, and that would be the impulse functions. And the impulse functions occur, they have a value of minus a, and they occur, they're staggered. Every value of t, but they occur at a time where it's displaced from 0, the first one, by tau. Y'all follow me on this, class? I'm just showing you the second series right here. Those delta functions all occur, right, at tau plus t, at tau plus 2t. Y'all follow me on that, everybody? Here's the reason I did this. I basically, without stating it explicitly, I said that this is really equal to two functions. It's some x1 prime of t plus x2 prime of t, right? Now that implies that there's a series x1 and x2 up here, right? If I did an integration with respect to time. Do y'all follow me on that? With me on that? Just hang on. All right, now this series is the one that interests me first. If I look at that, if I want to get x2, my goal is to get x of t in terms of an infinite series, all right? And that means, see, if I look at this for a second, and here I'm going to go back a step and remind you of the derivative, or what happens when we integrate delta functions. I did this on Friday, but I want to do it again. I'm going to say something. I know some of this stuff seems like it's not just building logically in the next step. I have to reach back and get some information. I'm trying to remind you about stuff you've had, but you may not use daily, so you need to be reminded of it. So, this is a little side note. If we have a delta function, first, what is a delta function? Well, a delta function by definition really is the derivative with respect to t of u of t, of the impulse function. Just think of that. If you have a u of t, the delta function by definition is the derivative of it, right? I could draw this out, and likewise, if you take the integral from minus infinity to any time t of delta of tau right here, d tau, you get u of t. Take a look at that. Remember, when you integrate a delta function, you get a value of 1 if the delta function turns on during the time of integration, right? If it doesn't turn on, it's 0. So it is a u of t. Y'all follow me? I'm just trying to make sure everybody's clear on that. Okay. Now, another thing about a delta function that's important is if you have any delta function, and I'm going to do it this way. I'm going to call it t minus some tau times f of t dt from minus infinity to infinity. Now, what I'm really doing here is I've got some f of t, and for the sake of everybody who's kind of just trying to get a little better picture of what's going on, this is t, and suppose this is my f of t. All right. In other words, it's smooth, continuous, and it exists. All right. And then I integrate that with this delta of t minus tau. Well, if this is tau, a delta function looks like this, right? This is delta of t minus tau right here, right? Now, if I take the product of that delta function times f of t, it is 0 everywhere except when the delta function turns on, right? And then you could make the case, this is really f of tau, because that's where it turns on, times the integral of the delta function dt, but that is just 1. Follow me? So that means this really is just f of tau. Now, I'm belaboring that point for a reason. Y'all with me on this? Okay. put the big yawn into your ear. All right, back to this. Now, remember when you got C of n there, technically what you should have done, you said that for all C of n, what that is 1 over the period, the integral, and it's over any period. I usually just put from minus tau over 2 to tau over 2. You have to integrate over one period. We can prove this if you want to see it after class. Of the function x of t, right? Here it's times e to the minus j n omega naught t dt. And that's how you get the values of C of n here, right? Y'all remember that? Here's where I'm going with this. We broke this up into two series, right? This series is all delta function, right? Now, when I take a look at this, this series right here, it is periodic, correct, class? And because it is periodic, I can say that this will be equal to a Fourier series. And that means I can say my x prime 2 of t is equal to a summation from n equals minus infinity to infinity. And I'll call this C prime 2 of n. It's the coefficients of the derivative series of x2 of t times e to the j n omega naught t. And again, this, it doesn't matter what I call this as long as there's uniqueness to it. Here the C prime indicates it's a derivative with respect to time series, and the 2 means it's associated with x2, not x1. Follow me? Now, this is equal to 1 over the period, the integral from minus tau over 2 to tau over 2 of that series. Now, what is that series? Well, between 0, or really between minus tau over 2 and tau over 2, which is about here, I'm assuming that the value of t over 2, not tau over 2. I'm assuming the value of tau is less than t over 2, but we could adjust this as needed. But this is really what? Minus a times delta of t minus tau. Isn't that how I would represent this functional form between minus t over 2 and t over 2? Y'all with me? It's just a delta function. The delta function erupts when t is tau, right? And it has a negative a value. Then I have to multiply this by e to the minus j n omega naught t dt. And again, what I'm trying to do is just show you that that coefficient there can be found doing this integration. Now here's the beauty of this. You'll start seeing it, I think. That's a delta function. I just told you when you have a delta function, you just find out where it turns on if you're doing an integration with the delta function, and just evaluate what's next to it at that time. Do y'all follow me? No fancy integrations necessary. So this is equal to minus a over t. And then where does this delta function turn on? At t equals tau, right? So I replace t here with tau. Y'all follow me? So it's just times e to the minus j n omega naught tau. And lo and behold, now I have my coefficient C2 of n, right? Here's the thing I didn't state at first. What I've shown you here implies that x of t is equal to some x1 of t plus x2 of t. In other words, because I see I have delta, whenever I have delta function, things are good. I'm taking derivatives, this is the goal, until I get delta functions, because I can evaluate the coefficients of a delta function series very easy. That's the goal. Now the second thing is, from here to the next step, since x of t is x1 of t plus x2, let me just write it out and show you. So this is equal to the summation of this is going to be x1 series minus infinity to infinity of c called C1 of n e to the j n omega naught t plus summation from n equals minus infinity to infinity of C2 of n e to the j n omega naught t. These two series represent x1 and x2. You can think of this as just x1 of t, and this one as x2 of t. Y'all follow me? Just to make sure. I'm just trying to make sure I don't leave anything out. All right, now when I take a derivative of these with respect to time, take a look what happens. If I take a derivative of those with respect to time, let me get rid of this. So when I have x prime of t, now, and I did this on Friday, that's a summation. I'm going to go right here. It's a summation from n equals minus infinity to infinity of j n omega naught here. That derivative with respect to t brings out the coefficient of t in the exponential. And then it's times c of n 1 e to the j n omega naught t plus, and then there's going to be the second series, summation from n equals minus infinity to infinity. And there will be a jn omega naught, again, because it's a derivative, of c, you can call it c, I can call this c1n, c2n, e to the jn omega naught t. Y'all follow me that? I'm just taking a derivative, and the derivative of these, because the c's are constants, just brings out the jn omega naught right here. All right? Now here's the key. This is x1 prime of t, and this is x2 prime of t. You'll notice the key feature is that coefficient, jn omega naught c2, is actually equal to what I'm calling C2 prime, all right? You all see the C2 of n prime? What that means is that C2 right here, or CN2, is really that CN2 prime divided by Jn omega naught. Now, that means I have to take this term here and divide it by Jn omega naught to get Cn prime. No, I haven't done a single integration by parts or anything like that. Y'all follow me? But now I've got the value of not only this series, the C of n, but for the derivative, but I got the value of the first series of x2. Do y'all follow me? So now I check that box. Now I need to get the value for the c's associated with the x1 series. Can you all see what I'm going to do here? I'm sorry if this is a bit, I'm cramped here, but just try to follow. Here's the x1 series, right? That's the first derivative of x1. I take another derivative, and what do I get with respect to time? Just impulses, don't I? Right? Because it's a square wave, right? I get impulses, so I'm going to do that derivative right here. I'm going to just put it up. And I think I included this in the actual notes that I posted, didn't I? Did anybody look at the notes? Yeah, this is in the notes, but it wasn't explained by me on Friday. So here, I'm going to use that series. I'm going to say, lo and behold, that crazy triangle series. If I take another derivative of that and I get x double prime of t, the prime just means a derivative with respect to the argument. Here it's t. And this is going to be x1. And what does it look like versus time? That's the origin. Well, what's the derivative here? And don't forget to go negative on this thing and try to draw it. When I go from 0 to just above 0, goes from what? 0 to a over tau, right? That's an impulse, isn't it? Yeah, so it goes like this. That's how we indicate impulses. This is really a over tau times delta of t, isn't it? Keep going. Where's the next impulse?
It's tau away.
Right. So I come tau away, and it goes down to minus A over tau, right? Now, then it repeats itself over and over, right? Just bang, bang. And really, we know that x double prime 1 of t it's a repeating series. Do you all agree with that? It's an infinite repeating series. And therefore, I can say it can be equated to a Fourier series. So I say my x1 double prime of t. As a matter of fact, what I can do is this. You all agree that this is my x1 prime, right? If I take another derivative of that, that just brings out a jn omega naught again, doesn't it? So it'd be jn omega naught squared, right? Times cn1. So this really looks like an infinite series from n equals minus infinity to infinity. And in this case, it's going to be jn omega naught squared times c1n times e to the jn omega naught t, right? Here's the part you got to pay attention. Are you with me on that? Now, this is the good. Oh, this is the important part. This right here, perfect. This right here is just like a CN1 double prime. It's just a constant. Do y'all follow me? Now, why did I say that? Because that means this is really this is a Fourier series, even though there's J and omega not there, because it's not a function of time. This is a Fourier series, right? That coefficient right there, I can call Cn double prime, and that's equal to 1 over the period, the integral from minus t over 2 to t over 2 of the function. You'll notice when I'm integrating this, I always, if I look at this over a length of time, if I go back far enough, then I hit a negative pulse here, and I hit a positive pulse here, right? It repeats itself. You all with me? Mm-hmm. Now, I'll guesstimate about here, there's minus t over 2, about here, t over 2, if we assume that, I mean, whatever t is, that's about halfway, right? And if we assume tau is less than t over 2, just making that assumption, then if we integrate from this point to this point, that is over a period. Y'all follow? But you can adjust this window when you do the integrations to get the coefficients. It could be anything you want. The thing is, with this window, I'm calling it a window, it's just a width. It's always going to be t in t wide, but you never want to have it start or end on a transitional point. You all follow me? That's the reason you move this integration starting point so it just catches the entire thing. Yeah.
If you're doing delta functions, then isn't the range kind of a moot point anyway?
No, because if you start right there, then you take half of the function. See what I'm saying? If it's a delta function, you start right where the delta functions exist. Well, let me see. Do I take half that value, the whole value? Do y'all follow? Because look, if you start here and stop here, then you have two delta functions that are both going northward. Follow me? You don't know what to do with that. So that the rule of thumb is always start integration, end in integration when we're talking about doing the tricks with the delta functions where there are no transitions. That's the goal. Got it? And otherwise you'll, I mean, there's the theorem. Do you remember Gibbs's theorem? For Fourier series, what it asymptotically approaches, if there's any kind of discontinuity, half the value. It's the average of the 2 points. But I don't even want to go there because that's more pure math that has no real application in the engineering world. Anyway, and I say that, oh God, I hope I don't hear. Anyway, what I'm trying to tell you is you always try to avoid areas where there's problems, and that is the transitional points. That's the goal. So back to this thing, you can see now I take this thing. Well, what is this thing? that functional form has a weight of A over tau, right? That's this X double prime right here, right?
Mhm.
And what is it really then? Let me erase this. Give myself some room. All right, what's the first one? At delta of what? Just t, right? And the second one? But it's minus, right? Minus delta of t minus tau, right?
Mhm.
So that's the x1 double prime, right? Now I have to weigh that because I want the coefficient. I want to say that's times e to the jn, actually it's minus jn omega naught t dt. And you'll notice this coefficient is this, so that's equal to jn omega naught squared, because we took two derivatives, times cn, and this is c1n, actually c1n. Are you with me? I'm not trying to bore you, I'm trying to just be clear. All right, go ahead and evaluate that integration. Believe it or not, I give this to people after I have a lecture. You'll be surprised how many don't. Just do it in your head. What happens? I know I have 1 over t right off the bat, right? And I have an a over tau. So I also have an a over tau. Now what? That turns on when? Equal 0. So what do? I evaluate what's next to it, multiplying it at the argument being 0, right? E to the 0 is 1. Keep going. When does this one turn on? Evaluate this at t equal tau. So it's e to the minus j n omega naught tau. You got it? Agreed? And that's equal to that over there. So you can see that what? C of n itself, since this is equal to this, I can divide by jn omega naught squared. And lo and behold, I have Cn1. Got it? Right?
Mhm.
Now, I got Cn2 somewhere. It's really this divided by Jn omega naught, right? Remember? So now my entire, I didn't do one darn derivative. After you do a few of these, you'll see the beauty of this. I hate doing integration by parts. I used to hate that, especially when they get to 3, you have to do it 3 times or something. Just used to irritate the heck out of me. Because primarily, when I was doing them, I was tired. Usually this is at the last part of the day you're doing these things. This avoids all that. If you have any kind of functions, we're taking derivative after derivative, will result in impulses. That's straight lines, like if you have a trapezoid. It's things that have like a t squared going up, and then t squared coming down, shark fin type things. Almost anything after you take enough derivatives, it's going to have impulses. The impulses are easy to evaluate. And therefore, when I look at this entire, remember the original series was that triangle wave that had a dead time, right? So now that wave itself can be gotten by saying it's n equals minus infinity to infinity. And now putting what the coefficients are, C1 plus C2, that's C1. I'm just going to call it Cn1 plus Cn2 times e to the jn omega naught t. And that's the beauty of this, because I take this and divide it by jn omega naught, stick it in there, and I take this and I stick it in there, and I got this series. I'm going to show you some more things about how we adapt these things to make sense of it. But you have to understand how to get these constants in the Fourier series. You know they're infinitely long. And we never use infinitely long things, but you can see a couple things happening here. Just look at this one right here. What happens is the value of n gets large. This is falling off as 1 over n squared, right? So when we're doing a Fourier series analysis, we may only need 10 terms here. You follow me? To approximate it. And it's a very good approximation. And we may only, that's falling off as 1 over j and omega naught. Again, we may need 20, 30 terms over there, but it's a very small number of terms to approximate what's really going on for Fourier analysis purposes. Do you know the real reason we do Fourier analysis? You're going to see it in this EMC lectures. This one or tomorrow's, next day. Well, Fourier series allowed you to do one thing. Remember the cosine and sine Fourier series? Well, you think about any kind of a periodic function you can break down into an infinite series or finite series of cosine. Let's leave it as cosines. Well, when I did circuit analysis for AC states, we assumed the driving voltages or currents were some magnitude like V naught times cosine of omega t plus some phase angle, right? Well, that omega might as well be n omega naught. And then what you can say is the input-output relationships. Remember how you did this? You took a time-varying cosine function, you turned it into a magnitude and an angle, didn't you, for a single frequency, right? Use that as the voltage and you got the output. Again, it was a magnitude and an angle, right? If you wanted to get the time domain output, you multiply that by e to the j omega t and took the real part, whether you know or not. And you basically got the magnitude times cosine of omega t plus the phase angle associated with the output. Do you remember doing this at all? And you didn't have to solve one differential equation. That was the beauty of this. So now if you have an infinite, you have a square wave or triangle wave, periodic going into any kind of a circuit or linear system, we can get the output of that without solving differential equations, just by getting the Fourier series expression. And more on this in a little bit. But anyway, getting back to this. So, now that I've done that, before I move off, I'd like to show you one simple one. An application of what I just showed you. To something simple. I'm going to give you a couple more, but I want to do one simple one before I move on. And I'll get to that trapezoidal waveform, the rise time, fall time, the standard one in a second. I just want to show you this. So you try to work with me on this and interact so we can see if we can do it. So here's a question. They always try to motivate students to respond correctly. I don't have a motivation tool. I don't have that kind of money. But I'm just going to try to get you guys to think about it and respond. So here's the function. It's going to look like this. This is t. This is x of t. And this is a. And this width, this is a symmetric triangle. Call the total width 2 tau. And that means this width and this width are tau. And call this t. All right. I want a exponential Fourier series expression for that. So I know it's going to be equal to a summation, right? Of C of n e to the j n omega naught t, n equals minus infinity to infinity, right? Now, what do I do based on what I told you using the derivative method? Well, your gut tells you take a derivative with respect to time, right? See where it goes. What happens when I take a derivative of that function with respect to time? What do I get? What?
Yeah, sum series.
Well, no, I'm just take a derivative with respect to time. What do you get? Derivative of the slope of the line, right? So from here to here, it's got a slope of a over tau, right? Just follow me on this. So here's tau. So it's just This slope from here to here, it goes up A over tau, so it's A over tau, correct?
Yeah.
What about from here to here?
Negative A.
Negative, right? And that's still minus A over tau. And then it repeats itself, hopefully. But you all see that, right?
Yep.
And this would be X prime. All right? Now what I'm getting where I'm going, right?
Mhm.
So that's one derivative. So here I can say my X prime of t would be equal to the summation of that with a j n omega naught times c of n e to the j n omega naught t, n equals minus infinity to infinity. Go ahead, what's the next step? Another derivative, right? We want to get impulses. What happens when I take another derivative of this? I'm sorry, what did you say?
You get impulses.
I'm going to get impulses, right? The first one would be at 0 time, right? And the magnitude would be minus a over tau. Keep going. Next one, at tau, but what's the magnitude? This is important. Right, minus 2a over tau, right?
Mm-hmm.
So now it goes down, I'm not going to be able to show this well, but it goes down to minus 2a over tau. Sorry if it's not showing up well, but y'all follow me on that, right?
Mm-hmm.
And then what? At 2 tau, what happens?
You get a positive.
Right. Y'all with me?
Mm-hmm.
Okay, I've got that nice, I'm glad I've got that, and that's a double prime, right? So I come over here, and you don't have to write this all the time, but that means my double prime series is going to be the series above, n equals minus infinity to infinity of j n omega naught squared, because I take another derivative of this with respect to time, and I take it times c of n e to the j n omega naught t. And here, I know that this is a constant on it. I mean, this is like my Cn double prime, correct? So that's a Fourier series. I'm going to try to throw this out. And if you take a look at that, I mean, what is this going to be equal to? This coefficient Cn double prime? Well, it's 1 over the period. It's got to be that for starters, right? And it's the integral of this double prime of x, correct? So if I do that, I'm going to go from minus t over 2 to t over 2. Then how would you represent this mathematically? You don't have to do this. You'll be looking at these and getting this just by inspection. Well, I can see the weight on this thing, the scale is a over tau, right?
Mm-hmm.
So I put an a over tau here. And the first delta function is a t equal 0, right? It's got a weight of 1 here. Right? What about the next delta function? It would be minus delta of t minus tau, but
So wait, 2.
2. Got to weight it 2 because it's 2a over tau, right?
Mm-hmm.
Keep going.
Plus delta t minus 2 tau.
Right, 2 tau. And this is all times,
Minus j.
right, minus j and omega naught t dt. Good. Agree?
Mm-hmm.
Just make sure you got this, because this is so good. All right, now evaluate the integral with me. So my C of n double prime is 1 over t, right?
Mm-hmm.
Times a over tau, right?
Mm-hmm.
Times a over tau. Then after that, do I write? Here's where people, oftentimes, I'm not sure, how do I do it? Go ahead, Jacob.
One.
It's gonna be 1 next, right? That's evaluating this times this, evaluating this arc here where t is 0, right? Because the delta function turns on at 0. What about next? Not you, Jacob. Isaac.
It's a tau, so it's 2.
Minus, right?
Yeah.
2,
Yeah.
right? Go ahead.
Activate the tau.
This time it's on the hour.
Maybe it does it for different days.
Yeah, tries to trip you up. All right, times what? I'm sorry, Jacob.
It's well, it's
E to the what?
yeah, negative j. All that
And omega naught
t.
how?
Tau.
How, right. All right, not Jacob, not Isaac. Go ahead.
It's going to be plus e to the negative j and omega 2 tau.
Right. You always been on this?
Okay.
Interaction helps. Believe it or not, you can hold things in. You're in the military, you know, so I learned something in the military. They're always, the pilots and the other people, I was on Eisenhower just as a weapons guy. And, I remember they always will ask you questions, not to insult your intelligence, but they want to hear your response with an intelligent answer so they know you got it. Because, I mean, you can easily zone out on some stuff. And when things go boom, they don't want you zoning out because, believe me, people do. All right. So anyway, that's the double prime, but what do we do to get just C of n? Well, I took 2 derivatives to get here, right? So that means I divide by jn omega naught squared. Follow me?
Mm-hmm.
So now I take this and I divide by 1 over jn omega naught and square it, and lo and behold, now I have my C of n. Okay, and that's how you do it. I'm going to show you a trick here that you're going to see over and over again before it's over. All right, now I see this crazy thing here. I don't like it, but I say, you know, this looks like something that maybe we can make work for us. All right. Remember, that's a j and omega naught squared here, so I'm going to show you something. I'm going to do it over here. I'm going to erase this. By the way, are we supposed to get rain all day today?
So,
Yes?
checking out.
Why did I even ask that? This is Alabama. You never know what you're going to get.
It's got till 6 p.m. and then we get like a hour-long break, and then it's supposed to start at 9 again.
Okay, so
Yeah.
here's a little Monday blues for you. So I have a boat, and I like to fish, and my wife likes going on just driving. But I don't like to haul it up to Martin just to haul it back to Auburn or wherever, because it's about 45 minutes up there, 45 back, sometimes a little longer. So you look at the weather, 12% chance of rain. So you can, it is not much of a chance. Come on, let's go. Instinctively, she says, no. Oh, we're not going to rain. Well, how do you know? Because it's Alabama. It always rains. And she was right. I don't care what AccuWeather says. In this state, if it's humid in the morning, don't go. It's not worth it. I mean it. And I get up before dawn and go, but sometimes it just doesn't work. Anyway, I would go drive up her stuff. So if I take a look at this, doesn't it look like maybe we could factor something? Like if I have this, doesn't that look like maybe 1 minus e to the minus j n omega naught tau squared? Let's see if that works. How about we just do it minus j n omega naught tau squared again? I get 1, right? I get minus 2 times e to the minus j n omega naught tau, right? And then I get plus twice those, or plus e to the minus j and omega naught 2 tau, don't I? You agree with that?
Yeah.
Keep watching, it gets better. Now, how do I know? Because I've lived through millions of things like this. When you're my age, you'll see these things, it'll be second nature. I mean, some of you probably saw that, but I'm just telling you, because some people don't. I said, how do you know it? Well, experience, that's the truth. You know, it's the only way. I mean, there are some people who just have minds, they see these things in an instant. But the way I see them is working with this stuff. So I get to that point right here. Y'all agree with me? And this is the next gear that goes into mind. Try to get in this function. Make it look like a function you understand. Now, anytime I see a 1 minus e to the minus j something, I'm always thinking factor out whatever that angle is by 2. E to that. So I'm going to go ahead and show you. This is going to be inside the square. So I'm going to take e to the minus j and omega naught tau over 2. All right. And I'm going to multiply it times e to the plus j and omega naught tau over 2. And then it's going to be minus e to the minus j and omega naught tau over 2 here. Now, I know that's squared, but you with me on that? Jacob knows where I'm going. Some of you probably do, if you, but not everybody. Y'all with me? I want to make sure. Were you in New York to get that cap, or you got a New York Yankees cap?
No, I got this from the New York airport.
From the airport.
Yeah.
I have got, every time I go somewhere, I used to get some kind of memorabilia from sports teams. I've got Oakland Raiders stuff, San Francisco, 49ers. I've got stuff from everywhere. I don't have a Yankees cap yet. And I used to watch the Yankees all the time when I was young because I came from Erie, Pennsylvania. And then I went to Penn State. At Penn State, we didn't have a Philly. We did have a Philly feed, but our main feed was New York City. So we watched every Yankee game. We had an old black and white set. I mean, they were available to us. But I don't have ball, and I've never been in their ballpark. You know, been in Pittsburgh, been in Cleveland, been never that. And that is the most famous park in the world for a lot of reasons. So I was amazed you have that. Anyway, back to this thing. We have this, right? How many know what I'm going to do right there? I just told you the sines, cosines, right? All right, think about this. What is sine of theta? Isn't that e to the j theta minus e to the minus j theta over 2j? What's that identity called? Euler's identity, right? You're going to use that one. You're going to use another one all the time. It's the cosine of theta, which is e to the j theta. And it's going to be what? Plus e to the minus j theta over 2. That's the cosine identity. These are forms of Euler's. Y'all remember that? You'll use these incessantly, all the time. So if I take a look at this and this, and I multiply this side by 2j, then you'll notice to fit that form, theta would be n omega naught tau over 2. Do you all see that? Sure. So what I can do is say, really, here, what I've got is e to the minus j n omega naught tau over 2, which I don't care about because it's, frankly, what that is a phase term. And then I have this, which is 2j times the sine of theta. The sine here of n omega naught tau over 2. Now, the reason I'm doing this here and now is because I'm trying to show you some things that I do all the time to make things easy on myself. I know what a sine looks like, right? I don't know what that looks like per se, this. I mean, I'm just not sure. I know what a sine looks like, and that's the reason I'm going here. Now, I'm not quite done either. You'll notice how I've taken this lump of stuff here and I've made it into that lump of stuff, right?
Mhm.
Of just this stuff. Well, but it's still divided by j and omega naught squared, right?
Mhm.
So I'm gonna work right here. If I divide this by j and omega naught squared, it's like just bringing j and omega naught inside the squaring, isn't it?
Mhm.
Y'all with me?
Yeah.
And now, anybody want to take a guess at what I'm gonna do? I mean, you could do one thing to simplify. Can't I get rid of those j's? Right?
Mhm.
This j and that j, or
Yeah.
they go away, right?
Yeah.
Let's get rid of them. Now, things are looking interesting. What if I divide top and bottom by 2? Getting better, right? Now, doesn't the argument of the sine appear down here? And anybody? Yeah, you were right, Jake. The sinc of x, this is one of the common definitions. Sinc of x is equal to the sine of x, right? Over x, where x is the argument, right? All right, so here, you all agree I could replace this right there by sinc of that function, right? Now, do you all know what a sinc function is? How many do? You don't remember? If you don't, it's okay. If you think about a sinc of x is this, so if you look versus x at the sinc of x, it actually does this. It has a value of 1. This is versus x, and it does this. Kind of just decays out. This is something you're going to run into over and over again. So this is falling off the proportional of 1 over x. Where's the first 0? The point where the function goes to 0. Just look at that. At 0, it has a value of 1. It's an asymptom. You have to take derivative top and bottom and evaluate it at once. L'Hopital's rule. But where's the next 0? I mean, that isn't a first. First 0 is when sine is 0, isn't it? Because x is monotonically decreasing. What makes sine 0? Well, sine of 0 is 0, right? Sine of pi. Isn't that right? So when x is pi is where the first 0 is. I'm trying to make sure you guys at least appreciate some of the finer points of the reason I'm doing this. Now the sinc function is an even function. I know what it looks like, and that's real useful in understanding and appreciating some of the EMC stuff to come. But a lot of this stuff is just preparing the way. So now I have that, and to get the final form, I have to multiply by a, and then divide by t and multiply by that, but I'm not quite down here. You'll see one thing I didn't do. See that tau right there? I don't need to multiply this by tau and then this by tau. So now this exactly matches that argument. And therefore this is equal to, I'm going to do it this way. I'm going to say C of n, there's my C of n, is A over capital T, small tau, and then it's times this business. It's e to the minus jn omega naught tau over 2 squared. And then it's times the sinc of omega naught tau over 2 squared. That's the sinc function. And there is a tau here. And you can see what happens is the taus cancel. That's my.
Tau squared or just?
No, I'm sorry. Here's what I should say. There's a tau squared there. Yeah, this is absolutely tau squared, and just the tau downstairs, all right? From over there, and you can see that that means there's one tau that survives. Do you all see what I'm doing here? Before I move on, Isaac, can you see it right there? Over here? All right, so that means I have this. I really have A times tau over T times that stuff, right? Now, what do you call tau over T if it's a square wave? Duty cycle, right? That's just the duty cycle. It's the percentage of the waveform that has a signal that's non-zero, right? When you divide it by capital. And that is the waveform. This term right here, that's just the phase. If I have e to the j 30 degrees and I squared it to the j 60 degrees, who cares? Its magnitude is 1. Here's where the magnitude starts dying off of that sinc function. It's dying off like 1 over n squared, where n would be the value, it's the coefficient of omega naught. Y'all follow me on this, class? All right, I needed to get through that. Now for my next trick. Now we get into the actual trapezoidal waveform, and why it's so important, and I'll get down to brass tacks too with you, but I gotta make sure you appreciate some of this stuff. Because we're gonna have more than enough time to get through the microwave engineering stuff, but here, this will really help you with a whole lot of stuff, because with Dr. Wimmer's book, the only thing he does is, well, the bandwidth's about 2 over tau. Oh gosh, it still bugs me. Don't use bandwidth. Take a look at the frequency response, because there's so much information there that you need as engineers. Some of you, I don't know which ones, but I'm going to guess some of you will work where you have to do things where you integrate systems. The higher up you go, especially as you get into more and more management, you have to see different parts of electronic systems come together, and they all have to be able to function without destroying each other. This is a big deal with the armed services, but now it's a big deal with the car industry. Years ago, I want to just tell you this quick story. So years ago, cars had things called points. They didn't have electronic ignition. You had to set it with a timing lock. Y'all remember that? Now that was basically, they had electromagnetic solenoids that basically caused the spark to fire at a certain time, okay? And that was something that was EMP proof. I mean, you could have dynamite go off, you could have a nuclear weapon. It would not affect that system because there was no electronics. So then they went to totally electronic ignition. You're too young for that. You at least have an understanding of some of this. Electronic ignition causes the car's cylinders to fire based on some solid state circuits that are digital in nature. And it's basically, it takes away the actual rotating, inductively triggered thing where you needed a timing like the settings. I'm not going to get through all of it. So then they brought in solid state electronics. They're made with silicon. The devices have FETs where they have, an FET transistor has a capacitive, it's really an oxide layer, right? And they pull up, and that's really a capacitor, right? Just keep that in mind. Capacitors go bad really easy when you put a high voltage on them, or you put an impulsive charge, or you cause the lattice structure of the oxide to tear apart, which EMP does. And so does other things. So anyway, this is at Dogburn, Virginia, the Naval Surface Weapons Center on the Chesapeake. So they build, this is just at the time where all the new cars had electronic ignitions. The old cars did. They build an IMPRIS facility. And this is to test things to see if an electromagnetic pulse from a nuclear weapon going off would cause any malfunctions with weapon systems, mainly nuclear weapon systems, but all. And I've been there. It's a big arch. They have a large capacitor bank, and they hit it, and it causes an electromagnetic pulse to form from a pseudo antenna. It's only its near field. That pretty much is a replica of what you would expect from a nuclear weapon if you were not blown up by the weapon. In other words, fairly close to it, within about maybe a couple hundred miles. And the IMPRIS facility, they warn you when they're going to fire and stuff. It's not loud at all. But there's a parking lot nearby, so they're doing this test. So the next Okay, people go out to start their car, about half of the cars or so, a third of the cars don't start. Taking back, well, the electronic starter is at fault. Get a replacement part. About a month, 2 months go by, they test it for us again. Now they warn everybody they're gonna test it. Thing is, some of these people don't know the connection between how far away you have to be from this thing before it'll destroy electronics. Which is interesting, because the government is very good at not telling people how far away to be. So they do it again, and again, these cars don't start. This is rotten pieces of crap, but they're not just like Hondas or Fords. They're everything that's new. And then some clever individual said, there seems to be a correlation between that thing testing and my car being destroyed. And then they figured out it was the EMP pulse that was destroying it. Now, if any of these guys did basic EMC and understand that if you get an propagating electromagnetic signature of field levels beyond a certain point, you're going to cause failures in electronics. They didn't do that. Now, this is just the ones they really noticed. There's probably failures all over the place, but this is the one they noticed. And I got really into EMC after that, electromagnetic interference and compatibility, because that ruined new cars. By the way, I might not, I don't want to get in trouble for saying this. Have you ever heard of some of the weapons that are called, they're non-lethal ways of stopping crowds, crowd control and all this? So all sorts of neat stuff. But one thing they don't tell you a whole lot about is military's ability to stop vehicles with something like I just described. Now, if it's a truly hard thing, you can. But they can knock, if they want, if they want to spend the money, they can knock out a vehicle, a car and stuff like this. Like if you're threatening the president of the United States or something like that, or some general, if they want to, they can bring electronic countermeasures to take your vehicle offline, unless it's a hardened vehicle or something like that. They can do stuff like this. The Russians, however, I got to hand it to them, they, either by coincidence or by design, they seem to get around all this. The Russians still have, to my understanding, and some of the very top-end MiGs, they still have vacuum tubes. Vacuum tubes don't fail with EMP. You know about this? At all. They are immune. Now, admittedly, they're not as elegant. They can't cram the electronics, but they ain't going to knock a MiG out of the air by an EMP pulse. And it's simulated or real. And with the Russians, like, I love this story. We spent about $1 million on a pen that were writing zero gravity. The Russians used a pencil. Why didn't I think of that? How can I be that? I got a host of things the Russians, I say Russians, I mean, a lot of these East Bloc nations did during the Cold War. They're super, and they're cheap. And we had spent millions of dollars on fuses and stuff for bombs going off. They'd put a big cement block and hang it, have a parachute, slow things down. When the cement block hit, a spring would just close and would go off. But they do a whole lot of stuff that we don't. Anyway, enough on that. I figured you guys deserve a crazy story, so there's a couple of them. Now, back to the real world and EMC while we're doing it. What I need to do is take this trapezoidal wave and turn it into a Fourier series, and then take that Fourier series and turn it into a single-sided cosine series. And I may not have enough time, but I'll give it a shot. You'll see why, because you want that spectrum. You want those C of N's. That tells you, the square of those tells you the actual power in the signal. Okay. So, and this is going to repeat, here's the PRI of that, or the period capital T. All right. Now, with this one, I'm just going to tell you. I take one derivative, I get a square wave. Follow me? And then I get a square wave that goes negative. Y'all follow me on that? I'm gonna do it over here. I won't draw so large. And it repeats itself. This is A over tau. Tau is going to be the rise time. This will be minus A over tau. And here, the actual length. Let me do it this way. Call this tau rise. And just call this tau, because it'll be consistent with what I'm about to give you. So this is tau rise. And this time here to here will be tau. And then it repeats itself. Y'all with me? What am I going to do next? Just take a shot at it. I don't have impulses, do I? I need another derivative, right? Correct, class? Sure. So I'm going to take another derivative of that, and I get this. And then this one occurs at tau, it's minus A over tau rise. Here it's going to be minus A over tau rise. And then it goes back up to A over tau rise. So that's going to be the double derivative series. Okay? Now that series I know will have a coefficient that I'm going to get. This is all going to get back to this trapezoidal equation. And this whole thing right here, that C of n double prime will be equal to A over tau rise. Now remember, the C of n is 1 over t, so I'm going to have a 1 over capital T as well here. Right? Then it's an integral from minus t over 2 to t over 2 of that functional form, and I took the A over tau rise out front. So it's going to be delta of t, then it's minus delta of t minus tau rise, and then it's minus delta of t minus tau, and then it's plus delta of t minus the quantity tau plus tau rise, times e to the j n omega naught t dt. And again, I'm just telling you that's the double prime, right? Because it's two derivatives, and you know I'm going to divide that by j n omega naught because I want just c of n squared, right? Because I took two derivatives. So let me just do that real quick. I'll divide it by 1 over j n omega naught squared, and that's c of n. Now you can see what's going to happen. I'm going to have A over tau rise, over t tau rise, 1 over j n omega naught squared. And then, well, this delta t turns on at 1. I mean, at t equals 0, so it's 1 minus e to the minus j n omega naught tau rise. Do y'all see this? All right, next one is going to be minus e to the minus j n omega naught tau. Finally, it's going to be plus e to the minus j n omega naught tau plus tau rise. You with me on this one? Anybody see anything I might do? Take a guess now. Here's where I'm always going. Try to make it into a sine, cosine, and then a sinc, right? The If it's a cosine function, it's not really a. All right, you see anything that might be done to do that? I'm always looking for tricks of factoring. Let me just tell you. Factor out 1 minus e to the minus j n omega naught tau rise, all right? Factor that out of this term, you get 1, right? Then factor that out of this term right here, you end up getting what? You get 1 minus e to the minus j n omega naught tau. Now, if you don't see it, you will. If I take 1 minus e to the minus j n omega naught tau and multiply it by 1 minus e to the minus j n omega naught tau rise, take a look. First term is 1, right? Now take a look at the terms that are left over. This one right here is minus j n omega naught tau. Right? This one is e to the minus j n omega naught tau rise. And the final one, where you add the exponents, is this one right here. It's a plus because it's 2 negatives. Y'all see that? All right, just hang on with me. Now, what do you think I'm going to do with that? Now that I'm going to be able to factor that. Any guesses? I'll put it down here. What do you think? Anything? Jacob? He's on. I'm going to take a look at this angle here, divide it by 2, and factor out e to the minus j n, or basically e to the minus j, half this angle out in front. Now listen. Then I'll get e to the minus j n omega naught t over 2, tau over 2, minus e to the minus j n, and I'm going to replace that with a sign. You with me on that? Same deal here. And then I got 2 signs, right? One here, it's got a tau. This has a tau rise. You can see I'm going to fuss with this. I'm out of time right now. I'm a minute over. I'm going to fuss with this until I'm making a couple of sync waveforms. I'm going to give you some stuff to look at and read here, but I wanted you to hear it from me in class why this is interesting. I know this lecture, generally people get a glazed over look like, all right, thus the story. But I'm trying to keep you guys on topic here. I'm really, you're going to see how all this makes sense as soon as we get into the frequency analysis. Now, Jacob has had me for signals, and you remember this, right? But you're going to appreciate this in a second. Did I have you in for signals? Okay. I'm sorry I didn't have more. Did I have you? No. No? All right. Well, you're going to get this stuff for a reason. You'll see the applications, the EMC, and many other things. I think you'll like it. Hey, if you got good stories about electronic failures and stuff, I mean, I'll tell you,